Welcome back to Physics 141 Online. I'd like to do an example problem that's similar to some that you'll see on your homework, and in particular I want to do this problem because it deals with the work done in a spring problem. And we really haven't done too much in class about that, although there's plenty of information in your textbook on this subject. So here's the question. How much work does it take for you to stretch a spring with a given spring constant of K equals 130 newtons per meter from an initial position 10 centimeters from equilibrium to a final position 20 centimeters from equilibrium? All right, and as usual, we're going to start with a sketch. I hope you're getting the hang of that in solving physics problems, that we always want to start with some kind of a sketch. There are very few problems that I would try to do without a sketch, because if nothing else, it helps me think about what's happening and clarifies the physical situation that the problem is describing. So here, I'm going to just imagine that there's a spring. I'm not even going to worry about anything connected to it because it says that I'm pulling on it. I'm going to stretch this spring away from its equilibrium position. Okay, so here is the spring, and there's equilibrium right there. And we always measure the x as the displacement as the distance away from equilibrium. So equilibrium position, where it's unstretched, is the origin. And then what we're going to do is stretch it from an initial position, x initial of 10 centimeters, and of course my scale might not work out perfectly, to an x final of 20 centimeters. X final is 20 centimeters away from equilibrium. All right, I'm not going to try to draw my hand here, but you get the idea that the spring starts out in its unstretched position at equilibrium at x equals 0. Then I'm going to grab it, stretch it to 10, and we want to know how much additional work is done when you start at 10 and go out to 20 centimeters. Okay, so in order to set this up, of course, here is the spring with the spring constant K. We know the K. We need to know the force, because remember that the work done, there's a couple of different ways of writing it down, but the work done for a changing force like this problem will be the integral of the force acting along the x direction times dx from x initial to x final. What does that mean? That is the area under the force versus distance graph f of x from a position x equals x initial all the way out to x final. And I won't draw that graph, but I just remind you what the expression is for this. And I'll remind you how to solve it, because in this case we want to know that fx that's in this equation is the force that you exert on the spring. Because notice, the question says how much work is done by you. How much work does it take for you to do? It does not say how much work does the spring do. It says how much work does it take you as an external person to do this. So we know an equation that's part of what we refer to as Hooke's law for springs that says the spring force is minus the spring constant times the displacement away from equilibrium. The minus sign reminds us that if we pull the spring to the right, it pulls back to the left. So if x is positive, then the force is negative. That's what that minus sign is for. But that's the force on the spring. Notice what we want to use in our equation for work is the force that you exert on the spring. And this here is Fs is the force exerted by the spring on you. And once we write that down in words, it becomes very clear that these two forces are third law pairs, right? Because one is the force that you exert on the spring, and the other one is the force the spring exerts on you while you're pulling on it. So that means, since these are third law pairs, that fx, which is what we want, is minus fs, because we know they pull in opposite directions, but they have the same magnitude. Since fs is minus kx, then fx, which is the force that you exert on the spring, is kx. It's minus a negative or a positive. Which means, now when we go to calculate the work that you do on the spring, we again write down this calculus-looking expression from x initial to x final of fx, which is now kx dx. So if we can evaluate this, we've solved the problem. K is a constant, all right, and so it is something that is just going to be treated like a number because we're given the numerical value for it. And the rule, remember the rule, when we want to find areas, the area under a simple polynomial type function is that if we want the area, we have to calculate what is called, so here if this integral, which again means area, from x initial to x final of some function ax to the n dx, what we do is the a comes outside because it's just a constant. We raise the power of x by 1 to make it x to the n plus 1, and we divide by that power, n plus 1. And then we have to evaluate that expression, that new expression, at the upper limit of x final and then at the lower limit of x initial, and we have to subtract. And that's what this expression means with the brackets around it. So I'll show that here. But that's the rule, and this process right here of going from the original function, which is the function you're trying to find the area under, and the final function, this is called integration. And if you're not already at that point in your calculus class, you will get there sometime in the not too distant future. So what do we do with the work equation? We just apply exactly this rule. What we've got in the work equation is actually k x to the 1, right? Because x is the same as x to the 1, so that this becomes k, right, x squared over 2, using that rule, evaluate it between the two limits, the different values of x, the extreme values of x, under which we want to find the area. And so this just becomes, you can see right here, k over 2 times the quantity x final squared minus x initial squared. And I could have left the k over 2 in there multiplying both those terms, but I just factored it out because it's present in both of them. So that notation with the brackets and then the upper and the lower limit means you take the upper limit, you take x equal to xf, plug it in here, and then subtract what you get when you take the lower limit. So that's exactly what I did here. I took kxf squared over 2 minus kxi squared over 2. So that's my result. If I didn't have numerical values, I'd be finished. So all I need to do then is to substitute in the numerical values, and here I'll emphasize again, this is the work done by you, the work it takes you to do on the spring. So k, 130, and once again I'm going to make a special appeal for you to keep the units in these expressions when you evaluate them, because if you don't, you run the risk of messing up your units. And this problem is a good example. Look at the x values. The equilibrium, the distance away from equilibrium, they're given in centimeters. And so if I plug in 10 squared, or rather 20 squared minus 10 squared, without the units, I would get the wrong answer because 10 and 20 are given in centimeters. So I really need to change units. So instead of 20 centimeters, I'm going to put 0.20 meters, and of course that's got to be squared. And then we subtract off the initial value of 0.10 meters because that's 10 centimeters, and we square it, and we see that when we get the value of 1.95, which comes from squaring those two terms and subtracting, and then the 130 over 2 is a 65 out here. Look at what we get. Newtons per meter times meters squared, which is Newton meters, and that is the definition of a joule. So we have 1.95 Newton meters, or 1.95 joules. In terms of the assess step here, at the very end of the problem, I don't have a good feel for knowing whether that's a large number of joules or a small number of joules, but at least we can say that the units are okay, because we got an answer for this work term in joules like we expected to. So I hope this is helpful as you work through these kinds of problems involving springs or involving changing forces that don't have constant values but change with position. And I'll just mention once again that this problem, because it asked how much work you do, we got an answer that was positive. And I guess that kind of makes sense too. We can think about that if I do positive work, it means that it cost me something to pull on the spring, right? I had to do work in order for that to happen. If we had asked how much work is done by the spring, then we'd be integrating not fx, but we would be integrating fs, and we would have gotten a negative value. And the reason is because while it's being stretched, the spring is pulling against that. And so the displacement would be to the right in my sketch. The spring force would be to the left. So if the problem had said how much work does the spring do when you stretch it, you'd get the same numerical answer, but you'd have a minus sign in front of it. So again, I will see you in class, and I hope that this is helpful.